In this video, we will look at geometric progressions, or GP in short, which is a series where consecutive terms have a common ratio. Some examples of a GP are listed here. The common point between these three sequences are that between the consecutive terms in the same sequence, we multiply by the same value. For example, in this first sequence, every subsequent term increases by a factor of 2. In this second sequence, every subsequent term decreases by a factor of 4. And in the third sequence, every subsequent term changes by a factor of r. In every GP, we can define two values. The first is called the first term, or A, and the second is the common ratio, which is the constant ratio between subsequent terms in the sequence. Once we have defined the first term and the common ratio of a GP, the terms in the GP will be U1 equals to A, U2 equals to AR, U3 will be equals to AR square, U4 will be equals to AR cubed. And we can rewrite these terms as, for U1, A times R power 1 minus 1, for U2, A times R to the power of 2 minus 1, for U3, A times R to the power of 3 minus 1, and for U4, A times R to the power of 4 minus 1. And we can see that subsequently, when we reach the nth term, Un will therefore be AR to the power of n minus 1. And this is the general formula for a term in a GP. And in this formula, n represents the position of the term within the sequence. Other than finding the individual terms of the GP, we can also find the sum of n terms in a GP, which we denote using Sn, and Sn will be U1 plus U2 plus U3 all the way until Un. Note that this definition is the same as that of the sum of an AP, although consecutive terms are being multiplied with the same common ratio. The sum of n terms is still an addition of consecutive terms rather than multiplication. As with the formula for the sum of an AP, we will also want to derive a formula for the sum of the GP. And how we do so is, first, we can write down Sn as A plus AR plus AR square and so on until we have AR to the power of n minus 1. And we can write it again by multiplying it with R. So we have R Sn, which gives us AR square, and so on until AR n minus 1, and finally AR to the power of n. Now if I call this equation 1 and this equation 2, I can take the difference between these two, because when I take the difference, all the middle terms will be cancelled out nicely. So if I take equation 2, subtract equation 1, I will have R minus 1 times Sn equals to AR power n minus A. And therefore, this gives me Sn equals to A R power n minus 1 divided by R minus 1. Or we can also factorize out the negative signs from within the numerator and the denominator. And this will give us A times 1 minus R power n divided by 1 minus R. You should note that both formulas are equivalent and we will be able to use either one to obtain the same answer. But as a general guideline, I would advise that for this first formula, we will use it when mod R is more than 1. And for the second formula, we will use it when mod R is less than 1. And in the sum of n terms in a GP, n again represents the number of terms to be summed. And to find out Un, we can take a difference between Sn and Sn minus 1. In addition to the sum of n terms, some GPs can also have sum to infinities. This is possible when mod R is less than 1. This is because the terms will become smaller and smaller as the progression proceeds. From the definition of Sn, we let n go to infinity such that s infinity equals to the limit as n tends to infinity of Sn, or a 1 minus r power n over 1 minus r, the r power n term will become 0, and therefore what we are left with is a over 1 minus r, and thus we have obtained the formula which is the sum to infinity for a GP. In example 1, we are given two terms of a GP, the 17th term and the 20th term. And based on this, we have to find out what is the common ratio in terms of x. So we know that U17 can be written as AR to the power of 16, and U20 can be written as AR to the power of 19. At the same time, we know that U17 can be written as 3x plus x squared, and U20 can be written as 24x power 4 plus 8x to the power of 5. Therefore, if I name this as equation 1 and 2 respectively, and take a division between them, I will have AR to the power of 19 divided by AR to the power of 16 equals to 24x power 4 plus 8x to the power of 5 divided by 3x plus x squared, which can be reduced into r cubed equals to 8x cubed, and therefore I get a common ratio r to be 2x. In example 2, we have the number 2.161616, and we see a pair of dots over the 16 at the back. This means that we are going to continue repeating the 1s and the 6 throughout until infinity. Therefore, this sequence is the same as writing 2.1616 equals to 2 plus 0.16 plus 0.0016 plus 0.000016, and so on. Now if I factorize out the 0.16, I will have 1 plus 1 over 100 plus 1 over 100 squared, and so on. So we can see that this is actually a sum to infinity, where we can use the formula a over 1 minus r. Therefore, we will have 2 plus 16 over 100 times 1 over 1 minus 1 over 100, which gives us 2 and 16 over 99. As with a AP, sometimes we are required to prove that a certain given sequence or series is a GP. And to prove so, we have to make use of the property of an AP. That is, the ratio between consecutive terms is a constant. Thus, for any given sequence un, we simply have to find un minus 1 and the ratio between them. If this ratio is a constant, then the given sequence is a GP. Note that we cannot take the difference between specific consecutive terms. Like for example, we cannot find out what is u2 over u1 and it is equals to 5, and u3 over u2 equals to 5, and conclude that it is a GP. We cannot do this because we do not know whether the subsequent ratios u4 over u3, is it going to be equals to the same number or not. Therefore, the only way for us to do so is to make sure that the ratio between the general terms is a constant before we can conclude that the sequence is a GP. In example 3, we are now given the sum of a certain series to be 3 minus 3 to the power of 1 minus n, and we need to show that this is actually a GP. So we know that Sn is equals to 3 minus 3 to the power of 1 minus n, and we need to first find out what is un, and we can use the formula un equals to Sn minus 1, which gives us 3 minus 3 to the power of 1 minus n minus 3 minus 3 to the power of 1 minus n minus 1, which is 2 minus n, and we end up with 3 to the power of 2 minus n minus 3 to the power of 1 minus n. And we should further simplify this equation This is the same as me writing 3 to the power of 1 minus n times 3 minus 3 to the power of 1 minus n times 1. And therefore, this term for un becomes 2 multiplied by 3 to the power of 1 minus n. Now with this, let's find out the ratio between un and un minus 1. Un over un minus 1 will be equals to 2 times 3 to the power of 1 minus n divided by 2 to the 2 times 3 to the power of 1 minus n minus 1, which is 2 minus n. And therefore, this ends up with 3 to the power of minus 1, or 1/3, which is a constant. Therefore, we know that since un over un minus 1 is a constant, Sn must be from a GP.